We talked about reactions of alkenes and we talked about Markovnikov rule. Okay, so the very first reaction we talked about is halogenation, and then we mentioned Markovnikov rule. Markovnikov rule will be applied onwards, and this relates to formation of carbocations or unsymmetric products. Okay, so now what did we say about halogenation? We said, let's say you have a double bond and you're adding bromine. The bromine will simply add to the double bond in an anti-fashion, not trans, anti-fashion. So whichever way you look at it, maybe you're doing chlorination. Bromine here is brown, added to a colorless solution. The solution stays colorless. That's a test for presence of double bonds. If there was no double bond, the solution would have been brown. Okay. Here you're adding chlorine across. Of course, if I were to show that the chlorines are added I would draw the chair and you will definitely see that they are anti. Alternatively, I would show the wedges where the one chlorine is at the back, the other one is towards you. Okay, I'm just reviewing what we talked. Now about Markovnikov rule. So let's say you're given this molecule and you're asked that it should react with H+. Let me specifically say HCl, which is what we're about to talk about. So let's say you're reacting it with HCl. One thing you need to know is that there is dipole moments pointing the electronegative chlorine. So this is partially negative, this is partially positive. So you push your arrow starting from the bond, and you also need to do that in OWL, otherwise it's not gonna, the OWL, the OWL website, homework website will not let you get it right. Start from the bond, finish on the atom. I think they should highlight. So you open up the bond, picking up the hydrogen, and this falls off as a leaving group. So Markovnikov rule states that in reactions where you're adding across the double bond, the more electropositives part of the reagent will add on the sp2 carbon that has more hydrogens. Obviously here there's no hydrogens, and this sp2 carbon has 2 hydrogens, so this hydrogen should go where there's more, which is here where it's CH2. So if you do that, you're gonna get a CH3, because this hydrogen right here will end up attaching on this carbon. Then on the other side you'll have one bond less, so we put a plus sign. So that's what we call a carbocation. That's what we mentioned last class. And of course I said as you pick up the hydrogen, the chlorine leaves. Start from the bond, point to the chlorine. Chlorine leaves, getting the 2 electrons. Remember here chlorine has 3 lone pairs. So once it gains the extra 2 electrons, it has 8 electrons. The valency of chlorine is 7, so it has 1 extra. So you have a negative charge. Alright, so the chlorine will come back because it's negatively charged. It's going to come back and attack the positive center because opposite charges attract, and this will be a product. So remember, your hydrogen was added here where already you had 2. You already had 2 hydrogens. So the hydrogen added there, the chlorine added there. This reaction is called hydrohalogenation. Okay, and it's coming up very, very soon. Let's see where it is. This is where it is, hydrohalogenation. So I'm gonna cover that first, and then I'll talk about hydration. So hydrohalogenation, it's the addition of HX across the diabond to produce a Markovnikov halide alkene, that is an alkene with a halogen. Reactivity is Hi is more reactive than HBr, which is more reactive than HCl than HF. Why is it so? The reason is iodide is a good leaving group. When iodide leaves, okay, or when you split this apart, you get I minus. I minus is big, so it's stable because the electrons on iodide have much volume to stay in there. So the better the leaving group, the more reactive the hydrohalide molecule like HI. HF, the F is small, the hydrogen is small, so there's a very, very strong bond between them compared to HI. Just like a skinny guy hugging a skinny guy, the grip is strong. Here, a skinny guy hugging a sumo fighter, there is less grip right there. So this would have been your I, this would be a H, so the bond is small. That's why iodide will readily fall off. Okay, and you want it to fall off for you to add the proton to the diabond. Okay, whenever you're using HBr, it needs to be done in the dark atmosphere to avoid radical reactions that usually give anti-Markovnikov product, the opposite of Markovnikov rule. But the same mechanism applies for other acids like sulfuric acid, phosphoric acid. They are all similar. So for us, we're going to emphasize this for addition except HF. HF is not commonly used in hydrohalogenation, which is addition of hydrogen and halogen. The X here could be Cl, Br, or iodide. Rarely do we add F across the diabond. So like I said, the process will involve Markovnikov addition. There's a CH2 here. There's a H on this carbon right here. So this hydrogen should end up where there's more, which is here. There's two hydrogens here. There's one hydrogen there. So this H should end up here. That's how you end up with a CH3. You started with a CH2. You used your pi bond to grab the hydrogen. You get a CH3. This carbon right here, now it's one bond less. It takes a plus sign. And then if this was HBr, okay, just doing the same thing as a blue arrow. If this was HBr, the Br would fall off. So the Br would come back to attack the positive center. You get what we call a alkyl halide. So that followed Markovnikov rule because the electropositive part of the reagent was added to the side where you have more hydrogens, creating a more stable secondary carbocation, which is later attacked by the nucleophile, which in this case is going to be the Br minus that fell off, for example, from HBr, okay, to get your product. So if I give you this problem and ask you, predict the Markovnikov product for this reaction. So what I will do, I'll show the hydrogens possible across the diabond so that I can apply Markovnikov rule, because we need to do Markovnikov addition. So this is the electropositive part of the molecule. So we start the arrow from the pi bond, attack the hydrogen, this opens up, okay, you have one hydrogen here, there's no hydrogen there, so the electropositive hydrogen here should add where there's more across the diabond, which is down here. And so what I gonna get is, because we had a hydrogen there, now there's gonna be two of them with this hydrogen added, and then the pi bond swung over attaching to this carbon, so the carbon up there is one bond less, so we put a plus charge, and then the Cl fell off during this proportionation of the reagent. When the hydrogen was pulled out, the Cl falls off. Remember, Cl here has 8 electrons around it, so when you break it, it's gonna be a standalone anion with 8 electrons around it. Chlorine has a valency of 7 on the periodic table. It's on the main group 7. This is a Cl. So now you have 8. So you have a negative, 4 more charge of negative. So the Cl will not want to stay by itself because it's negatively charged, going to be attracted to the positive center. It's going to play the role of a nucleophile. Nucleophiles attack positive centers. They like positive centers. Nucleus of an atom is positively charged. Okay. Phile is just loving. So the negative charge species will love to attack the positive center. So you end up with an alkyl halide, which comes from the Markovnikov reaction. Notice that this is a tertiary carbocation. Okay. All right. So let's go back to another reaction here called hydration. It starts here, I think. Yeah, it starts here. So hydration reaction. Hydration is simply addition of elements of water. Addition of elements of H2O. So you're simply adding an H on one side by Markovnikov process and an OH on one side. Okay. So the first step for hydration is gonna be attack of an acid. For hydration reaction, you're gonna need acid catalyst. Okay. It's the addition of elements of water across the double. We know that. And then what do you get? You get an alcohol from an alkene. So you're moving from an alkene, you get an alcohol, for example, in presence of an acid catalyst. It requires an acid catalyst. If not, then the reaction might not happen. So if you're gonna add water across the double, you need an acid catalyst, which will help the reaction to go faster before you get your alcohol. You're moving from your alkene, you're going to your alcohol. Okay. So you need the acid catalyst. So the first step, you use your pi bond. For example, if we're gonna use the propene molecule as an example, you use your pi bond to attack the positive charge. Again, it's still gonna be Markovnikov addition. The H plus of the acid, back there, here you have a CH2. You have a CH2 right here. Here you have a hydrogen. So the H plus of the acid should go here. And then here you should have the plus charge. Okay, so you'll have a CH3 here. And then the plus charge next side after Markovnikov addition, because the H plus goes to where they small. And then, only then, will the water molecule come to attack the positive center. So you get this molecule, after which you're gonna take out the hydrogen, the extra hydrogen from the water that came with the water to neutralize the oxygen. The oxygen gets a plus charge because you use its lone pair. End product is gonna be an alcohol. Okay, so you always do this step, is called proton transfer. Now, to repeat, first of all, the double bond should attack the acid catalyst as a nucleophile to get the Markovnikov carbocation. So you had CH2 here, you accepted an extra hydrogen, you get CH3, that's a secondary carbocation. Only then will the water come in as a nucleophile to attack. So you get, because you use the lone pair, the oxygen, you get a plus charge on it. You get what we call an alkoxonium, an extra water molecule, because you have lots of these molecules in the flask, will take out the extra hydrogen from the oxygen, neutralizing the oxygen, and you're left with now two lone pairs on the oxygen because the bond broke towards the oxygen and the alkyl part. This is an alcohol. So you started from the alkene to the alcohol. Examples. So let's say you have this ring and then you are told to hydrate it in presence of an acid catalyst. I will do the same process. I have a hydrogen here. Here there's no hydrogen. 0 hydrogen. We still have to do the Markovnikov addition. So first I would add the hydrogen of the acid catalyst on the side of the double bond that has more, which is down here. So I'm gonna get 2 hydrogens down here after the Markovnikov addition, and this bond up here that did not have any hydrogen will bear a positive charge because it's 1 bond less, 1 valent electron less, and only then will the water come to add itself using its lone pair, attacking the plus sign. So the water here plays the role of a nucleophile. Like I told you in last class, nucleophiles can be negatively charged or neutral. In this case it's neutral. In this case the alkane is neutral. The alkene and the water are playing the role of nucleophiles, attacking positive centers. So once the water attacks, then you're gonna get the water here, but now the oxygen will be a plus charge, and of course there are 2 hydrogens there. I'm not going to show them, but you don't want to stop there. There's lots of water molecules in the flask. We do the last step that I just mentioned, which is protonation, proton transfer or deprotonation, to neutralize the oxygen. So you deprotonate the positively charged oxygen and give it the 2 electrons that made the bond, which helps to neutralize the oxygen. You end up with an alcohol. So you will have moved from the alkene to the alcohol following Markovnikov addition. Okay, I'm just gonna call it Markov addition. All right, that's an example of hydration reaction. We talked about halogenation. Now hydroboration. This is a type of hydration, but it's gonna be anti-Markovnikov. Why do we call it anti-Markovnikov? It's gonna add the OH and H opposite. Okay, so hydroboration, you're adding a hydrogen, and in the process of the mechanism, you'll be adding a boron. But now the boron will be kicked out by water, and that's where the hydration comes in. So the final product is an anti-Markovnikov alcohol, because we are doing anti-Markovnikov hydration. There are 2 steps in the mechanisms. So first, you are reacting the alkene with BH3, and then the second step, you're using hydrogen peroxide and a base. It could be potassium hydroxide or sodium hydroxide. The electrophile of boron B atom, the electrophile is the boron atom. H is more electronegative than boron. Now, you might not get that. Let me just explain visually. So let's say you have a double bond, okay? You have a double bond. So if the double bond has 1 more substituted end, let's say you have this kind of double bond. As you can see, the left side of the double bond is more crowded. You have an isopropyl group, right? There's a CH3 here, CH3. This side is bigger. Here you only have babies. So whenever you're using boron, because of the size of boron, okay, the boron will tell itself, I have to align myself on the side of the double bond that's not crowded. This side is less crowded. The left side of the double bond, this side is crowded, this is less crowded. The boron will align itself on this side, and then all you're simply doing now is to pick up that hydrogen, and then this bond comes down. So that's what this is showing. So that is called the transition state, where you want to break this bond. You want to form this bond, attach the hydrogen to this carbon. The R group here, for example, is what I put here as a isopropyl group. Okay, this is the isopropyl group. There's a CH3 here. There's a CH3 there. This is just a group that I put there to represent the R group, the big group. Okay, this is big. That forces the boron to be on the other side. So you want to form this bond, you want to break this bond, and you want to form this bond, and you want to break this bond. So I'm using the word you want to. So you are in the process. So this is called a transition state. I usually don't ask you to draw it, but you need to identify it. If you see it, you can know it's a transition state where bonds want to form, bonds want to break. So if you do that, let's say you break this bond and form this, and you can push these arrows the other way around and then break the pi bond to attach this. So simply put, you have a hydrogen here if you're using propene as an example. Okay, I'm not using this one. I just used this to illustrate the transition state. This time I'm using propene as an example. So you had one hydrogen, now you'll have two hydrogens. Notice that the hydrogen is adding, this hydrogen is adding on the side where there is less hydrogen, and that's where you have the anti-Markovnikov addition. Okay, so that's the anti-Markovnikov addition. Because in real sense, we'll have expected this hydrogen of the reagent to go where there is more, where, for example, here. Okay, so the BH2 adds on the other side, and then you repeat several times until you get what we call Br2. And then remember, there was another reagent here called the peroxide, which will come and add on to the boron. And of course, that knocks out the boron. In some way, it's going to knock out the boron. Don't worry about the mechanism. Do not worry about the mechanism. I will not test you on it. I just want you to know that the first step is anti-Markovnikov of the mechanism. Okay, anti-Markovnikov addition. You see, this hydrogen in black adds where there's less, and then the BH2 will go where there's more. That's anti-Markovnikov. Would have expected this hydrogen to go where there's more. But when you do this reaction with propene, eventually the alkene will be changed to an alcohol. Notice that the OH is on the outside. You get a primary alcohol. It's sitting on a carbon which is bonded to one other carbon. So it's primary alcohol. It's on the outside. That is the anti-Markovnikov product, because the hydrogen of the first step was added where there was less. So you get propanol, while in hydration here, where's the hydration? Yeah, in hydration here we got 2-propanol, because this was formed where the hydrogen was added by Markovnikov fashion. The hydrogen of the acid went where there's more to get CH3 from CH2, and then you attack the secondary carbon, you get a secondary alcohol. But for hydroboration, you did the first step, anti-Markovnikov addition, so you get a primary alcohol. So it's anti-Markovnikov hydration of alkenes whenever you're doing hydroboration. Okay, let's do some examples. So let's say you have this molecule, and I tell you that you are reacting it with BH3 and hydrogen peroxide in presence of a base. What's the product? Now, the clue to you is that whenever you see a reagent, you should click in your head or have flashcards that will let you remember that this reagent, this recipe should be hydroboration. Now, once you notice that it's hydroboration, you have to know the rule that it does anti-Markovnikov hydration, which means the alcohol will end up on the side that has more hydrogen. The OH group will end up on the side that has more hydrogens. The H will end up on the side where you have less hydrogens. So across the double bond here, there's no hydrogen. Here, there's 2 hydrogens, which means OH will end up here, I'm just giving you the shortcut for hydroboration. The H will end up here. It's still hydration because you're adding elements of water. Okay, OH and H. Eventually, that's what's going to happen with this reagent. So to predict the product, I'll simply draw the skeleton, which has 1, 2, 3 carbons, but now the OH will go on the side where there's more hydrogens. These 2 hydrogens are still there, so the OH goes where the 2 hydrogens were. This is the carbon that I'm marking here, and then here there's no hydrogen. You end up with 1 hydrogen on there. Okay. Now the other rule that I need to mention is that this reaction adds H and OH on the same side, so we call it syn addition. Syn addition. Now to illustrate that, I'm gonna use a ring. So let's say we have this ring, and then you are adding BH3 peroxide and a base, sodium hydroxide, potassium hydroxide. To illustrate anti-Markovnikov addition, at the same time to illustrate syn addition of H and OH. This is the product I'll draw. Okay, in fact, I'm going to modify this ring to put a CH3 there, so that I can illustrate these 2 points using the same molecule. So here I do have a hydrogen, so that's where the OH will go if I'm to do anti-Markovnikov addition. The OH ends up on the left side. The OH ends up on the carbon having more hydrogens. Here you have 1 hydrogen. Here you don't have any hydrogen. So the hydrogen will end up where there is less hydrogens. So one would have put it here. So that's anti-Markovnikov addition. H of the reagent, after the whole mess of a mechanism happens, the H goes where there's less hydrogens across the double bond. The other part of the molecule goes where there's more hydrogens. So in this case, it's hydration reaction, so we put OH on there. Now, I've illustrated point number 1. What about syn addition? We said syn addition is where the H and OH adds on the same side. Okay, that's what syn addition means. Same side addition or same phase addition. So to do that, to show that, I'm going to use wedges. So if the H and OH added from the top, then I need to use the shaded wedge, which means the other existing groups will be flashed to the bottom. So I have to modify these bonds and put them away. Okay. So if these 2 were added, so these 2 were added from the top face addition, then I use the towards or the shaded wedge, which the existing groups, which is the hydrogen and the methyl group, will have to be flashed back, both of them. That shows syn addition, same side addition. So it's anti-addition, first of all, anti-Markovnikov addition because the H goes where there was less, and then syn addition because whatever is added on the same side. Okay, same face of the molecule. Okay, which means it's very, very possible for you to have the opposite, where the hydrogen were added, the H and the OH were added from the bottom face. So I'll put the hashed bond for H and OH. Both these shows syn addition, because you can see elements that were added eventually are on the same side. Next is hydrogenation. So here you're just killing an alkene to make an alkane. Okay. You know, alkenes and alkynes are unsaturated. So we will show how hydrogen adds, but it's going to require a catalyst, in this case a metal catalyst. Okay, so let's say you're using platinum, palladium, nickel, or rhodium. Those are metal catalysts. They help the hydrogens to add on the alkene because the hydrogen bond is very strong. You're going to need something that will break it apart before the individual hydrogens are added across the double bond. It's still going to be adding in syn fashion. The two H's are added from the same side, so it's syn addition. Both atoms are added on the same face of the double bond. So to explain that, for example, if you have this molecule and you're adding hydrogen gas, like I said, the HH bond is very strong, so you're gonna need some metal catalyst, either platinum, palladium, nickel, rhodium. Anyway, this bond will be cut across and you're gonna add the hydrogens across the double bond. So you will have either the metal flashed up and the two hydrogens that you added will be on the same side. Of course, there's another hydrogen here pre-existing. So this H2 is that and that. You killed the double bond, so you end up with an cyclic alkane where you started with a cyclic alkene. So remember what we said. Addition of hydrogen atoms is reduction. So this hydrogenation reaction is a reduction reaction because you're adding hydrogens across the double bond. So how does it happen? The first step is hydrogen absorbs onto the surface of the metal catalyst. Remember I said the metal catalyst could be platinum, palladium. For myself, I prefer nickel. Nickel and palladium, those are my two best. I've never used platinum. So the hydrogen, the H2, adds onto the metal surface. So you see it's added. It used to be a molecule, but now the covalent bond is cut across and the individual hydrogens are added on the metal surface, and now they can be added on the double bond. Okay, and the catalyst is going to be recycled for another cycle. So the catalyst is recycled for another cycle like this. So you will have killed the pi bond and made an alkane, and it's syn addition because these hydrogens are added from the same side. In this case, they are added from the bottom face. So you see they are drawn to be on the same side. So this is an alkane product that came from an alkene, and this is just the metal catalyst that helps to break apart the hydrogen covalent bond. Examples again. So let's say you have this ring. You have an ethyl and a methyl, and you're adding hydrogen gas in presence of a metal catalyst or nickel. So again, we have to show that this is doing a syn addition. Markovnikov rule not applied here. We are not applying Markovnikov rule. So let's say you're adding from the bottom. So the ethyl group will be flashed up because it's a opposite push. The methyl group will be flashed up. Both of them will be flashed up because we are doing syn addition. And then the hydrogens that were added from the bottom, both of them at the same time from the metal catalyst complex. But you still have the other option where the hydrogen atoms will add from the top, which means the existing alkyl group or substituents will be flashed down because the hydrogens added from the top face. Okay, so again, these two products illustrates syn or same face addition, same side addition of the reagent, which in this case is hydrogen, in the reaction we call hydrogenation. Okay, you can start with this in presence of hydrogen gas and a metal catalyst. You're gonna get that. So that's the alkene. We go to the alkane. I hope you notice we added hydrogen gas, because here there are 2 hydrogens. You're gonna end up with 4 of them. Remember, each carbon must be surrounded by 4 bonds. Sweet. That's not the only addition reaction. Another addition reaction will involve oxidation, which is simply addition of oxygen atoms. That's one of the definitions. We discussed about this in chapter 1. So one of the reagents that we use is potassium permanganate. It's purple in color. Okay. So once you add the potassium permanganate to an alkene, it's gonna turn to brown black. Why? Because manganese oxide, the solid manganese oxide, will be formed as a byproduct, and as a result you're gonna add 2 OHs across the diabond. And I think this reaction must be done in cold temperatures, not hot temperatures, because if it's hot and in presence of a base, it cuts the diabond into 2 pieces. It overdoes the reaction. So an example of this reaction is, well, like I said, potassium permanganate is purple. If there is an alkene in there, after a few minutes you're gonna see a dark solid. That's a test for presence of alkenes. So let's see. So this is the reaction. So you have an alkene, you're adding potassium permanganate dissolved in water, you're gonna get a diol. These are byproducts of which I don't ask for in the test. These are just byproducts, but they're important because your visual detection of the brown color using your eye, brown black color, will tell you that yes, you have a diabond in there. So simply put, you start with the diabond, react to potassium permanganate, you should get a diol. Okay, the reaction mechanism goes through formation of a cyclic ester, and then the OHs are added thereafter. I'm not gonna go through the mechanism. It's just gonna maybe discourage you or take a lot of time. So let me give you examples, which is what I require for your quiz and test and homeworks. So let's say you're given that. I forgot to tell you that it should be syn addition 2. So let's say you're given this molecule and you're told to react with potassium permanganate, okay, which is in the presence of water. The product of this reaction will be a diol, which means 2 OHs attached to the molecule. You'll either gonna add the OHs from the bottom, where the pre-existing groups are flashed up. There's a hydrogen here. That's what I'm calling pre-existing. These are CH3. The CH3 is now flashed up. Again, I told you it should follow syn addition 2. Or you'll get it like this. So I'm showing what we call stereochemistry. If stereochemistry is not needed, you'll be told. So CH3, H, this time we are adding our 2 OHs from the top. Now, without showing stereochemistry, without showing top-bottom stuff, and doing the same reaction, potassium permanganate, of course it's diluted with water, one would simply just draw your molecule with 2 OHs, just like that. Here, no stereochemistry shown. Stereochemistry means these wedges things. No stereochem shown. Okay, so this reaction is actually dihydroxylation. These guys are hydroxyl groups. There are 2 of them, so we call it dihydroxylation reaction. and we're using potassium permanganate. There's another reagent that does that, which is osmium tetraoxide. Osmium tetraoxide. So if I do the same reaction, okay, that's a 6-membered ring, and then I'm adding osmium tetraoxide, the same reaction happens, syn addition. So without showing stereochemistry, this is what you'll get. But if you have to show stereochemistry, okay, if the question requires you to show stereochemistry, you have to show syn addition. The OHs will be added on the same side. So that's my CH3 right there. It's this one and this one. You know I don't like showing hydrogens. You have the other option of adding the OHs from the bottom. Okay, this is showing stereochemistry, showing the wedges. So still, it has to be syn addition. You're adding the two OHs on the same side. It's dihydroxylation. Okay, so there is a reaction that splits double bonds across. So let's say you have carbon containing alkyl groups. If you are doing what we call ozonolysis, it's still a type of oxidation reaction because you're adding oxygen across double bonds. It's still oxidation. It's called ozonolysis because you're using ozone, and lysis because you're using ozone to break down a molecule. So this line implies you're just breaking apart. The shortcut is to just cut the double bond apart. If you were to cut the double bond apart, then you would get these two looking molecules, right? Using the R groups are generic groups. But now you don't stop there. You add oxygen across. That is a shortcut. The mechanism is beyond your scope. Okay? Now, if you're using ozone and zinc, the aldehyde part stays. I repeat, this is very important. If you're using the ozone, step 1, zinc, step 2, usually it's zinc chloride, HCl. So that's the HCl, it's an acid, and this is just zinc now. So if zinc is the second step, and you end up getting an aldehyde, you know, this is a ketone. I hope you remember your functional group. This is a ketone because there's a carbon there, and a carbonyl in between. This is an aldehyde because there's a carbon here and at least a hydrogen attached directly to the carbon. If you're using zinc as a second step, the aldehyde stays. If you're using hydrogen peroxide, this is a strong oxidant. It's a strong oxidation reagent. So the aldehyde will not survive. The ketone will stay the way it was. The aldehyde will be formed all right, but it's going to go one more step and get oxidized to the carboxyl group, the carboxylic acid. So instead of stopping at the aldehyde, one would want to put an oxygen in between the carbonyl and the hydrogen. You get the carboxyl. You get the carboxyl group. Otherwise, you can call it carboxylic acid. The carboxylic acid. So it's very important you pay attention to the second step. Using peroxide, you go all the way to the carboxylic acid. So like I said, I will not discuss the mechanism. It's just beyond your scope and it's just gonna confuse you. So I will not test you on the mechanism. Instead, I want us to do some examples as usual. So let's say I have this molecule. Okay? And I'm doing so let's say I'm doing ozonolysis. So let me put an arrow here and say ozone and second step I'm using zinc in presence of an acid. All you're simply doing is cutting the double bond across. That's the best shortcut you can use. So you'll end up with these two pieces. But because it's oxidation, so we've done the breaking down, the lysis part. Because it's oxidation, I would use my shortcut to simply put oxygens there. Notice that these are the same, so it would have been okay for you to say 2 equivalents of that molecule. I just flipped it up. Now what if what I had was, okay, you'd say you get the same product if the second step here was a peroxide. You get the same product because both these are ketones. There's no aldehyde in there to be oxidized further. Both of them are ketones. So what if you had this molecule and we use ozone? Second step, you're using the mild oxidant zinc. Again, shortcut, cut it across. Okay, you get oxygen there, and then this bottom part will have the 2 oxygens down there. Notice that all these are ketones on the second molecule. That's a ketone functional group, CC carbonyl, CC carbonyl. But here there's a hydrogen. Here there's an hydrogen. So this is an aldehyde part on the right. And on the left, we also have an aldehyde. Okay, because we are using the mild second step, the aldehyde survives. Oh, but if we had the same molecule and I'm using on the second step, I'm using hydrogen peroxide, which is a strong oxidant. Okay, this is a strong oxidant. If you're using hydrogen peroxide, now it's different because I still gonna get the 2 pieces, all right? So I'm gonna get the ketone part at the bottom, right? This part, but the top part, this top part right here should have given me an aldehyde. I'm saying should have, but it will not stop there. This guy should have given me an aldehyde, but notice that you're using a strong oxidant, so the aldehyde will not survive. It's gonna be oxidized further to carboxylic acid functional groups. So again, keep note on step number 2, whether you're using zinc or the peroxide. All right, we use alkenes to make polymers. Poly simply means many, and polymers are made from simple units called monomers. They are the building blocks, just like you'll make a wall of a house using 1 brick. Okay, the mer part is just a structure or a compound. Refers to a compound. So you're making a long compound using small compounds or molecules we call monomers. So the process that we follow is a radical process, and it's called free radical polymerization. For example, that's how you make polyethylene from ethylene, from ethene actually. This is made from ethene, the smallest alkene possible. If you polymerize this in presence of a radical, you're gonna get this monomer, which is this ethene is the monomer, repeated so many times. So we'll just say this bond stretches to the left and extend to the right so many times, and refers to the number of times the monomer was joined like a chain. Okay, so same process for when you use propene or when you use butene. These are plastics. They're used for packaging, in Walmart paper bags, in pipes, and all those. Okay, we talked about radical reaction, and we said there are 3 steps. There is initiation, where you make your first radical, and there is propagation, where you make more radicals, and there is termination, where you stop the process, you cap or join 2 radicals. You don't end up with a radical in step number 3. Okay, so that's exactly how the polymers will be made from alkenes. It's a type of addition reaction because you're losing the pi bond and adding something onto the molecule that had the pi bond. So initiation, step number 1, we use our radical initiator. So that's what I used here as R dot. We are trying to make this group here, which to me I'd say this R dot. So we usually use a peroxide to help the process go. We use it as a catalyst for polymerization. So the bond between the peroxide, an organic peroxide contains 2 carbons. It's not the same as hydrogen peroxide that you use to clean wounds. Instead of the hydrogens, you have the carbons. So break apart the bond between the 2 oxygens. It's homolytic cleavage because you're moving 1 electron. It's common for radical mechanism. So take 1 electron to one side, 1 electron to the other side. You're gonna get RO radical and RO radical. There are 2 of them. That's why we have 2 RO radicals. And then use the radical that you made to attack the alkene. You do the same thing. The pi bond, this is a sigma and the other one's a pi. The pi is the weakest of both, again, because it's formed by side-side overlap rather than head-head overlap for the sigma. So that's the one to open up. So again, use fishhook arrows because you're moving 1 electron. So you simply try to make a bond between this carbon and the oxygen by bringing the 2 electrons together, because a bond is made by 2 electrons. So you make that bond using this electron and that one, and then these other electrons donated to the other CH2 on your right, so it ends up there. Notice that now you've added your RO radical onto the alkene, you've broken the pi bond, you get a carbon-centered free radical. So you use this radical for the next step. Okay, so I would call this process number 1 initiation, and then this should be the propagation. This is where propagation begins, and it happens several times. So you get another radical. That's a characteristic of propagation. In initiation, you make the first radical. In propagation, you get more radicals. So you use this radical, okay, to attack the alkene, just like we did before. So join these 2. There's an arrow missing. Join this carbon to this CH2. Break apart the pi bond, the sigma bond stays, the other radical goes on the other side. You are adding 2 carbons onto what you already made on the previous slide right here. So you end up with 1, 2, 3, 4 carbons. So this is the 3rd and 4th carbon. This is the 1st and 2nd carbon. They are joined together. These 2 electrons combine to make a bond. That bond is somewhere in between here. And then you do the same process. This time you're joining another alkene, ethene, so to speak. Looks like you're trying to make polyethene. So, sorry, this arrow needs to go all the way to meet the other one. So you're using the radical here to combine with the other electron from the pi bond, and this other electron goes to the other side, flies onto the other CH2. So you will have 1, 2, 3, 4, that's this part, and then 5 and 6 attached. This red fishhook arrow and the purple one makes a bond in between, and so on and so on and so on and so on and so on. So you can keep on adding your ethenes. Okay, in the process, you're gonna make polyethene. You make polyethene. Why? Because you used ethene as a monomer. This is otherwise called polyethylene or polyethene. Okay, so to terminate, you'll get like the longest, the chains, these chains. So let's say, for example, you have this chain with the radical. I'm not showing the CH, the hydrogens. Combining with another chain. Oops. That's ugly, but you get what I mean. Combining with another chain. If these two guys meet, then you're gonna get the very long. So I'm gonna say CH2 is gonna be repeated so many times. You get a very long polymer. Okay, where this N could be 1,000 times writing CH2 1,000 times and so on. It's a long chain. So that's a process of how you make polymers. Now, the polymer can end up chewing up itself. Like there's a snake, I think somewhere in Texas, that it gets older, it starts, or gets hungry and it's starved in the desert, it starts chewing itself and then it dies. So the polymer can coil and then deprotonate itself, takes out a hydrogen from one of the CH2s. You get this, and then this one could in turn react with an ethylene. Notice what you're doing. The polymer was straight, now you're adding an ethylene on the backbone. So that's how you get branching. Sometimes one would want it branched because it tends to help the molecule be flexible. If it's so straight, it becomes stronger, but if it's branched, it becomes weaker. So the result is a complex branch polymer, like a branch polyethylene as shown here. Okay. So how would you know the number of branching? How would you know the length? There are instruments that do that, but that's beyond your scope. But the amount of branching is determined by the number of monomers you're adding. It's determined by the reaction conditions you are heating. It's also determined on the concentration of the reactants. So you can control the number of branches, the length, and the physical properties of the polymer you want. And that's what companies like 3M do when they make their polymers. Now, let's talk about conjugated systems. To remind you, conjugation simply means where you have a pi bond next to a single bond, or a double next to a single bond, double next to a single bond. It could be on a straight chain, or it could be in a ring. Like this one is conjugated, but not fully conjugated. Benzene ring is fully conjugated. In fact, it's aromatic. You have double bond, single bond, double bond, single bond, double bond, single bond. So the single bonds where I'm pointing. Now, whenever you have conjugated systems and you do addition reactions across the double bond, you might get rearranged carbocations. Okay, the carbocations that results could be different because of resonance. One would still want to apply Markovnikov rule whenever you are doing addition across conjugated system, but the dictation of the major product, what determines the major product is the stability of the carbocation intermediate. And there are two ways you could there are two types of products you could get from conjugated system, either the 1,2 addition product or 1,4 addition product, where the 1,2 refers to where the H and the halogen went, for example. The 1,4 could refer to where the H and the halogen ended up. Now I've talked too much, but you'll better understand this by looking at the process. So let's say you're adding HBr. Okay? Let's say you're adding HBr. I'm going to ignore the blue arrow for now. So again, we want to follow Markovnikov rule. So the hydrogen is partially positive because there's dipole moments that points toward the bromine. The electrons that make the bond reside closest to bromine than hydrogen. So I would expect the pi bond to attack this hydrogen. Okay? So where this hydrogen ends up where there's a CH2 rather than where there's a CH, because that's Markovnikov rule. The electropositive part of the reagent ends up where there's more hydrogens on the sp2 carbons of the double bond. So you grab that hydrogen, don't stop there, you have to lose the Br. So if you do such an addition, the CH2 ends up being a CH3 because it accepted the extra hydrogen from the reagent. And then this carbon, sp2 carbon, is one bond less, so it takes a plus charge. We talked about that. The other product that will be formed will be Br minus because it fell off. If you are reacting this conjugated system, it's conjugated. Double bond, double bond, single bond. If you add the HB on this conjugated system, this is what you'll get. The Br falls off. Okay, so the H goes where there's more H's. You get a plus sign. These are carbocation, and it's not just a regular carbocation because there's a double bond to the carbocation. Remember, we call this an allylic carbocation because it's resonance stabilized. In an earlier lecture, we talked about this allylic carbocation. So the Br that fell off is gonna come back and use its lone pair to attack the carbon center. So you get this product. Now this is called 1,2 addition. Why? Because the CH2 accepted the hydrogen. And now we are showing the Br at this point. So if I was to just show what was added from HBr, you see a hydrogen is added on the first carbon, the halogen ended up on the second carbon, so it's 1,2 addition. Now, unfortunately, or fortunately, this double bond can move over by resonance. You're gonna get this carbocation. It's still gonna be secondary allylic, just like this one was secondary allylic carbocation. But now remember, in the first step we added our hydrogen here, right? That's where we added our hydrogen in the first step. Here, Markovnikov addition, the hydrogen went where the CH2 was, so I'm showing it here. So the Br that fell off at this point delayed to attack, so the carbocation rearranged in this manner or in that manner. This is just a resonance arrow. Now the Br now comes in after the rearrangement to attack the plus sign. So the hydrogen was added here, the Br ends up there, so this is 1, 2, 3, 4. Notice the groups that were added on the first carbon and the fourth carbon, so it's 1,4 addition. So the 1,4 addition products usually happen when there is heating. So we call it a thermodynamic product. Okay, 1,4 addition products are thermodynamic products because they arise especially when there's high temperature. The 1,2 products are called the kinetic products. They are spontaneous to be formed, they are easily formed, and they usually formed at colder temperatures. So 1,2 addition product is kinetic, formed from cold temperature reaction conditions. 1,4 additions are usually the major whenever there's heating. Both of them can show up, but the kinetic product will be the major product, like high percentage yield, like 70% of kinetic at 0 degrees, 30% of 1,4. At 70 degrees, 80 degrees, 90 degrees, high temperature, the 1,4 addition product, this guy probably will be 70%, while this one will be 30%. Okay, so using the 70 and 30% idea, you can get to understand what major and minor product is. The major product is what's formed in high amount, the minor is formed in less amounts. All right. Now, what if you have such a molecule? You see this one now, there's a problem because now you have one side that is highly substituted. Okay. There will always be both 1 2 and 1, 4 products from conjugated alkenes. I defined the temperature, can define which one is the major, which is the minor, whether you are going thermodynamic or kinetic. The only time a single product will dominate is if the carbocations have unequal stability. So that's the only time you'll see one product. Otherwise, you'll always see mixtures. Okay, now look at these double bonds. This double bond right here is less substituted than this one. See how these double bonds are surrounded by an R group there, an R group, and an R group. So it's tri-substituted. This one is tri-substituted. And the only R group I see across this double bond is this one, the rest of the molecule to your right. So this double bond right here is mono-substituted. By rule, what we call Zaitsev rule, the more substituted double bond is going to be the more reactive. Okay? So I would expect this side of the molecule to be more reactive than this side, because this one is more substituted. You see, I see an R group there, an R group there, and all this will be an R group. So this is tri-sub. The only R group I have here, considering this left double bond, is all this thing will be taken to be an R group. So this side is mono substituted. So I'm gonna erase this. You can pause the video and write if you want. So assume that we react the double bond that is less substituted. This is mono substituted to the left. Assume that we react this with HBr. So same Markovnikov addition, H goes where there is more. So the hydrogen will end up here. You still have the CH2 right there. I don't want to show it. So I'm going to get rid of it for purposes of clarity. Okay, so H ends up where there is more hydrogens, and this carbon right here will be one bond less, so put a plus side charge. Notice that the C plus is bonded to two other carbons, so this is a secondary. It's secondary allylic because there's a double bond next door which can do resonances. So if you push resonances, you're gonna end up with this, because now this carbon will be one carbon less. The double bond ends up there. Of course, the byproduct, after taking out the hydrogen from the acid, the byproduct is Br minus, which will come back as a nucleophile. Notice that after the resonance of the first carbocation, you get a tertiary allylic carbocation. Remember the rules of carbocations. We say that tertiary carbocations are more stable than secondary, more stable than primary, more stable than CH3. So which of these do you think will give you a lot of products? This is secondary, this is tertiary. Both of them are allylic carbocations. Of course, based on the ranking, the tertiary should win, because that carbon, that C plus, is stabilized by inductive effect and also resonance, of course, which is also here. Let's say that there are just 3 groups. It's tertiary, so there are 3 groups donating electrons towards the C plus, making it even more stable. So I would expect that once the bromine attacks, the 1,4 addition will way predominate the 1,2 addition. Probably you only even just see the 1,4 addition product. Not mentioning the temperature here, just the structure of the carbocation intermediates helps us to define who will be the major. Now let's give examples. So let's say you have this molecule. I don't like showing hydrogens, but for reasons of teaching, I'm going to show it. And we are adding HCl. Draw the 2 possible products and tell me who will dominate. So again, I see that the double bond down here is bonded to 3 R groups. Going this way is be taken as an R, going that one as an R, going this one as an R. So this double bond right here, that double bond is trisub. This one right here only has one R group, which is just the rest of the ring. So this is monosub. So which of these is more reactive? Obviously, it's the one that's trisubstituted. So I'm going to use that. Okay, I'm going to use that to accept my proton. And then this falls off. Remember, you're still going Markovnikov rule. So if you're attacking using this pi bond, the hydrogen of the acid should end up where there's more. Okay. So here you have one hydrogen, you end up with two hydrogens. Probably this came from the HCl. And then up there, you're going to have a plus sign because now this carbon right here is one bond less. Okay. And then the byproduct is a Cl minus. Notice that this can do resonances. Let me find another color. If we do resonances like this is the product I'll get. The double bond will be formed in between and there's going to be a plus sign out there. Now notice that this is a tertiary allylic because the C plus is next to a double bond. This is a tertiary allylic carbocation. After the resonance, I get primary because the C plus is bonded to one other R group, which is this whole mess down here. This is primary, but it's still going to be allylic carbocation. Okay, so which of these is more reactive? Now, if the Cl comes to attack this is the product you get from the resonated carbocation. Okay, remember there's a CH2 here. There's a CH2 there. There's a CH2 here. It's the same CH2 here. Okay, now if this happens, where's my red pen? If this happens and chlorine attacks here, the product will be this. So which of these will dominate out of these two products? Obviously this will dominate. If there's gonna be a mixture at all, this is gonna be the major. Why? It came from the most stable tertiary carbocation already, and then this will be the minor. We will continue from here.